So we have seen that using HNF form, I can solve these problems like Ax equals to b for integral solutions. But why HNF form works and what is the intuition behind? Let us look at the concept of lattice and how HNF captures the lattice that is generated by A. First, let me define a definition called additive group. What is an additive group? It has an origin, it has a 0 point. A vector is in there, then also its negation must also be there. If two vectors are there, their sum must also be there. Additive group is generated by a1 to am if you have two m vectors and you just take their integral combination. A group is called lattice if it can be generated by a linearly independent vector a1 to am. They are all linearly independent and the vectors are called basis of S. Let's look at what happens in the case of our original matrix and in our HNF matrix. So if this was our original three vectors and we try to draw the lattice generated by these three vectors. If you do that, you will find that these are the points, dark points, where we have a lattice. Okay, these are the points when if you use them as a b point, then the b vector, then there will be integral solution. Okay? And if you do the HNF form, it may not be surprising to see that the lattice generated by the green vector is same as the vector generated, the grid generated by the red vector. HNF preserves the lattice generated by the original matrix. So now there's a natural question comes along. If a group S is generated by to A1 to AM, then S is lattice. Okay. So if let A1, AN be columns of A, without loss of generality, let us suppose A is a full row rank matrix. It just spans the whole space. And we can convert A into HNF form B0. And since the columns B are linearly independent, okay, so S is lattice. So there was a requirement that A1 to AM be linearly independent. And if A1 to AM are not linearly independent, it's okay. There's an important observation comes along. Let's suppose there are two different matrices. I give you A1, A and A prime, and they are both are full row rank matrices, and with different HNFs, okay, B and B prime, yeah, respectively. If A and A prime generate the same lattices, then their HNF form should be the same B and B prime. This is amazing because this allows us to have some sort of a canonical form of these matrices. The reverse direction is very trivial. If you B prime actually defines your lattice, so therefore you can easily say that it's a trivial statement. If they are same, then they are generating same lattices. What if they produce the same lattices but they have different HNFs? We are going to prove that that cannot be the case. So let's suppose you have two matrices, A and A prime, and they are converted into this B prime, and then the idea is that they generate the same lattices. Let be written as beta ij, means beta ij is a ijth entry of the matrix B, and similarly we define beta prime ij. Consider I be the row where the B and B prime are different. Before that, all the entries are same at the jth column. So we say Bij is the first entry when things became different from B and B prime, and we're going to prove that that cannot be happening. That cannot be possible. So pictorially, you have these two matrices, and in which you have this entry Bij and B prime j are now different. And let's suppose Bii prime and Bii, we have this situation, the Bii is greater than equal to B prime ii. It can be anyway, but we just choose that one is greater than equal to another. In either both the cases, you will generate the contradiction. So now we say, look at the Bj and B prime j, these two column vectors. In these two vectors, you can say that they are sitting on the same lattice. All their integral linear combination should also produce the elements of that lattice. Okay, so if we subtract them, then again we get something which is on the lattice, and you can see that everything from here to here are same. So if you subtract them, you produce 0 0 0 0, and only this time, this point onwards, B and Bj prime, Bj and Bj prime will have a different non-zero values. So therefore they cannot be produced by the linear combination of the vectors before these guys. Only vectors after this can contribute to produce the difference of bj minus bj prime. Okay, so there has stated that they're a linear combination of bi to bn. Okay, only these vectors, or you can say that this side also, but just for building the argument we choose the one side only. Now we do is bij minus b prime ij. Since this is being generated by these vectors, and all these vectors, only bi has non-zero value at the top row, therefore the difference of these two must be integer multiple of bii. Okay, so now we can derive the contradiction. Since this guy has to be smaller than this guy, and this guy has to be smaller than this guy, right? And I am assuming that this is bigger than this, so means this guy and this guy both are smaller than this guy. Okay, therefore they cannot be integer multiple of this, therefore there is a contradiction.